Good morning. I'm delighted to be here, and as you heard my colleague Rahul talk, I'm also from Cambridge Consultants. Our purpose is to help clients create breakthrough innovations. And it's really exciting for me because I head up the global AI capability, and we do a lot of technology innovation in that space. And I've brought some thoughts around neuromodulation here today, and I'm looking forward to sharing them with you, and of course, some conversations on your comments at the end of it all. So, I think it's a perfect time for digital feedback based on the trends and technology that are happening. And they're really under three pillars. One is digital transformation, and the next is the growth of digital biomarkers, and then advances in AI technology. And I'd like to reflect a little bit on all of them. The first one, digital transformation, has really been put into high gear by COVID, and it's really forced us to use data to create insights that we can act on. For example, digital transformation has enabled us to use AI to plan vaccine delivery efficiently, to study the coronavirus's characteristics, and make sure we underpin supporting our healthcare delivery system in distribution of vaccines. Also, digital biomarkers are very important because they allow us the ability to quantify data and use it, and run analytics on it. So digital biomarkers are so a biomarker is a biological molecule that's found in the body that's indicative of a process, either in normal or in an abnormal situation. And a digital biomarker is any data that can tell us about the physiology or behavior in the system, as long as it's collected by a digital device. So that includes implantables, it includes digestibles, it includes portables. And by collecting digital data, we can then act on it and use it to inform other parts of the process. The next thing I'd like to talk about is there have been so many advances in AI technology that are enabling us now to look at the next generation of neuromodulation. In this field, technology changes so rapidly, it's actually quite hard to keep up, frankly. And so we at Cambridge Consultants actually have a regular tech watch that we offer some of our clients to keep up with everything that's going on. And that team helped me pull out three key trends, which I think are important in this space. The first one is a focus on humans. And that is more about how do we create AI that enables humans and maybe AI and humans to work in teams together. So it's about AI being more explainable and interpretable, which also allows us to think about how do we consider these aspects and balance them against trade-offs in performance maybe, depending on the situation. Another important part of it is, can we use AI to take humans from in the loop to being on the loop? So maybe there are some processes that can be automated reliably in a trustable way so that we can then put the human expert in as an observer, as somebody who is going to pass decisions when the AI algorithms cannot make them. And thirdly, the next part about human focus is about human-machine understanding. And that's very exciting. It's an area of our research as well. And it's about looking ahead to see, can AI be used to study human behavior and emotions? And so we have a better understanding of humans, so AI and humans can team better together in the future. The next trend is about evolving architectures, and this is about mathematical complexity. So while we see the pace of innovation in the mathematics of AI increasing rapidly, you also find that we're seeing a trend towards general purpose models. And what that means is you can use a particular version of a model in many scenarios. For example, we have a transformer architecture that now can outperform specialized models of previous generations that were created to handle specific use cases. In fact, these transformer models can outperform them and analyze videos and audios and point clouds. And this means we've got many more ways to use AI in many different scenarios. And finally, the last trend I'd like to talk about is the advancement of hardware platforms on which we can run AI. So you've all heard of the supercomputers from NVIDIA and the GPUs, but now we also see the growth of neural accelerators from companies like ARM and who are looking to enable the deployment of AI on very small, low-power chips. And this is very exciting because it means you can put AI in different scenarios. You can put it closer to the data generation source. And that's quite important in this situation of neuromodulation that I'm going to talk about shortly. Oops. Next slide, please. Sorry, I've lost the connection to the slide controller. But as it comes up, what I'd like to do next is to show you how we can use these trends and the power of AI to close the neuromodulation loop. Maybe now. Okay, thank you. So here's a typical loop. I'm sure all of you are very familiar with it. So there's an implant at some part of the nervous system, and from that we can sense signals. So once you sense signals, you get a measured signal, and then you can process it to get a process signal that gives you information about the process you're looking to modulate. And then that can be used to adaptively change stimuli to intervene or in the process and change how change the process and the outcome. And so in this loop, there are some important questions to ask. The first one is, where is the implant? As Peter pointed out, it's placing an implant in minimally invasive surgery is actually a completely non-trivial process. It's hard to see, and you need to know exactly where it's placed. Secondly, which signals contain the relevant information that you're going to use to control the feedback loop? And if you can get those signals, can you extract the information? That's really important too. And if you can extract the information, can you classify the event? If you can classify the event, can you predict the event? But really, because it's really about predicting the event, it's great to say, well, it's happening now, or it happened a few seconds ago. But to be able to do something about it, we'd like to predict the event. And finally, can we create the appropriate stimulation? And last of all, when and where should the stimulus be delivered? And it turns out you can use AI to answer all of these different questions, and that allows you to close the loop around this process. So what can AI do? So you've seen AI being used to diagnose conditions using image interpretation. We've seen it in treatment planning, in outcome prediction, in evaluation. But in this specific loop, you can use AI to improve surgical visualization of implant placement. You can use it to accurately and reliably detect symptoms. You can use it to detect biomarkers with very high predictive accuracy. And you can use it to interpret whether activity is pathological and where the target is, that's the source of the issue. And then you can plan optimal stimulus delivery for closed-loop stimulation. So let's look at all these questions, and I'll show you some examples of how this can be done. So the first one, and this is about surgical visualization enhancement. Now, if you've seen an ablation, which is often used in minimally invasive surgery, you'll know that it generates a lot of smoke during the process, and it's kind of hard to see what's going on. But you can actually use AI to unpick this distortion. And you can create an image like that. And that's very powerful. It uses state-of-the-art generative adversarial networks to do this. And we can unpick distortion from images, which gives us better insight into implant placement. Here's another thing we can do with AI. So once you collect biomarkers, and you find you want additional information, you can augment that information using, for example, biometrics, which are collected from sensors placed on the body. This particular sensor is set up to measure human stress. So you can combine it with neurological signals and create a richer data set that can be used to create interventions. And we actually do this in other industries. You're all familiar with autonomous vehicles, and here's an example of how we do it in that space. On the top, you see a camera image, which is of a scene as viewed through the driver's vision. Below it, you see a depth image, which we call a LiDAR image, which measures how far things are. And you can combine them both. They've got different resolutions. They've got different spatial and temporal variations. You can put them together, and you can make a composite image. And actually, we do that. And when you have that composite image, you've enriched one image with the information from another, and therefore, you can now detect events more reliably, more accurately. So then we can move on to event detection if you've got the right amount of information in it. Shown here are a set of EEG recordings from multiple channels. And on the right side of the slide, you can see it's a digital pathology image. It's actually of a slide where we're looking for tuberculosis bacteria. And we use AI to find the regions of bacteria so we can monitor whether treatment is progressing appropriately. But we can use the same idea in detecting events, and we can train deep learning models, neural networks, to look at EEG signals and figure out where events are occurring. So that's actually really powerful, because now if you know where the event is, you can look for signatures that cause the event. So it's very powerful and allows you to extract insight. So let's see how that's done. Because if you can actually predict an event, it's valuable in creating proactive stimuli to manage events, right? And so, for example, if you knew a storm was coming, you'd be prepared, like we all check the weather. It's the same idea. I showed you how we can detect events, but what if you could predict them? And you say, well, in 30 minutes, something's going to happen. And you can do that with deep neural networks as well. And that allows us to inform our loop proactively as we look to feedback these signals. Now, you may say to me, great, I'm sure those models are really complicated. I'm sure you trained them on hundreds of GPUs, and so this is really not practical. So let me show you something else that's interesting as we think about closing the loop. Because once you've got the ability to predict when something's going to happen, you can feed it back. So how do you feed it back into the neuromodulation loop? There are multiple ways. One is if you need a lot of processing power, like the block A, you can move the data onto the cloud, crunch it, and send it back. But here's the problem with that. First of all, you can run complex models, so that's great. But there is this whole issue around privacy, around robustness. There are issues around latency, and there are issues around just transferring a lot of data, which from a small implant, which means considering how much power has to be put into your design of that implant. So then there's another option where you don't send it all the way to the cloud, but you send it to maybe an assist device like a smartphone, which has more processing power. And there you probably can't run as complex models, but you have more processing power. But what's happening with this trend of creation of neural accelerators, you can now, these chips are becoming so effective and they're operating at such low power that you can move the intelligence to the edge. We call it edge computing or embedded, and you can embed the intelligence into the neural implant. And if you can do that, then suddenly the intelligence is very close to the data, so you can action on it and you can get the information that's required to act on closing the loop in a more effective manner. And here's an example of how we do that. So on the screen, you saw the digital pathology image that I showed you. It's actually a fairly large image. And originally, we trained this algorithm on the cloud and had 70 billion floating point operations to do the inference. And then what our team did is they looked at reducing the complexity of this algorithm without compromising the performance. And what we've done is then brought the complexity down to about 4 billion floating point operations. And with this increase in efficiency, computational efficiency and efficacy, you can run it on a smaller computational engine. When you do that, you don't need the cloud at all. And so actually this algorithm, which searches for tuberculosis bacteria, doesn't run on the cloud, it just runs on a smartphone. And so so this is actually very exciting because it means you can put this data processing engines closer and closer to the neural implants. We can then take it further because now once you get the insight, creating the reliable stimulus that's going to create the desired outcome, we can look there at creating complex and adaptive stimuli. It turns out I did a PhD in cochlear biomechanics, so I know about this problem quite well. What happens in auditory transduction is waves that reach our external ears are converted into neural information. And that process is a highly nonlinear, adaptive process that breaks up the sound into components, and each of the components create a signal that's adaptively varying depending on the intensity of the stimulus, depending on the frequency of the stimulus. And that's done in the cochlea, which is the inner ear. And now you can train models that take in the speech and break it up into those components, as though there was a cochlea in the middle, as though the basilar membrane inside is moving at different frequencies. It's quite marvelous. And when you do that, now we've got the right set of complex stimuli that we can generate and then use them to go to the next step of delivery. And finally, at the end of it all, we do need to deliver a stimulus. These stimuli are complex, and there's a lot of research nowadays that shows that events, neurological events are sometimes generated by networks that are sometimes created or sometimes temporarily disabled. And so if you knew what the networks are, which you can do with artificial intelligence, you can plan delivery, you can plan whether you want to recreate a pathway or remove a pathway, in the process of which you can stimulate targets in a beneficial way, and also not create non-beneficial stimulation. So you also get more power efficient when you do that. And getting here is really what allows us to close the loop. So, if you look at the whole picture, we can use AI all along this pathway, all the way from implantation to measuring signals, to processing them, to predicting events, to creating stimulation parameters, and delivering them. And this is really the way closed-loop neuromodulation, I think, is heading. And I do want to say before I end that we shouldn't forget, as we look at the excitement of the technology, that there's a human in the center, and this is really about them. And we can underpin this delivery, personalized delivery, using human-machine understanding, where machines can understand whether the human's actually getting relief. And I'd like to draw an analogy, a bridge to understanding, how we set the temperatures in our homes. All of us like temperatures at different amounts of different level settings, depending on where you live, depending on what you care about. And so just the same way that we can adjust our homes to be comfortable, we ought to be able to adjust these delivery loops to be comfortable to patients. And for that, we need to sense how the human in the loop is doing, how the human to who is the center is doing. And AI can be used to do that as well through the field of empathetic AI, where we look at comfort and understanding human emotions and behavior and state. So looking ahead, I think the technology trends do favor a lot of innovation, so I'm really excited to talk about it. And it is powered by the predictive capability of AI. And finally, adaptive network neuromodulation is, I think, the way of the future. And I'm glad to be challenged. I'm glad to talk about it. So please do get in touch, and I look forward to a good discussion. And once again, thank you, Peter and Ash, for having me.